Now with this topic, you get a very important equation that you have to use in many of the questions. And before I do anything, let me draw a circuit over here. And this time, when I'm going to draw the source, when I'm going to draw the battery, I'm going to draw the internal resistance as well. Alright, so this is the battery, and across it, along with the battery, I'm going to connect the internal resistance. Now this whole thing makes up the battery, this whole thing. So we represent this thing with a dotted rectangle. This whole thing makes up the battery, because the internal resistance is also a part of the battery, or it could be any source. Now that completes the battery, and now I'm going to complete a circuit over here. Let me connect a resistor, and then I'm going to connect a voltmeter across the resistor. So this is a circuit that we have. So let's say the EMF of the battery is 10 volts. Let's assume, like, we are representing, first of all, we are representing the EMF of the battery by E. That is the EMF. But then the thing is, the potential across the terminal potential would not be 10. It would be slightly less than that. Let's represent that by V1. And we know, like, V1 would be something like 9.5, 9.4, 9.6, something like that. And the potential across the resistor, which has the resistance capital R, is V2. And the current that is being drawn from the battery is, let's say, I amperes, capital I. Now, first of all, this theorem, what does this theorem say? Let me write down the statement along with the circuit before we do anything with the mathematics. This theorem says maximum power when internal resistance equals load resistance. In simplest words, if I try to convert this into an expression, into an equation, then I can simply write down this thing. In order to get the maximum power, the load resistance should equal the internal resistance of the battery. This is what the theorem says. That's it, period. End of discussion. Whenever internal resistance gets equal to the load resistance. Now, what is the load resistance? Load resistance means the external resistance. It would be an appliance. It could be a fan, could be a light bulb, it could be a motor, it could be a plastic toy, it could be anything. What is small r? It is internal resistance. You cannot change that. You can't change capital R. You can just replace the appliance with something else, but you cannot change small r, because that depends on the very battery itself. Now, what is the expression to find the power across the resistor R, which is a load resistor? The expression is power dissipated, or the output power, equals I squared times R. We keep studying that in O levels, the formula for power dissipated across the resistor I squared R. Okay, it's not a new one. We are already familiar with it. Now, consider this thing as a circuit in which you have EMF, which is in series. Here you have two resistors which are in series, small r and capital R. And we already wrote down this thing, if you could remember, in the internal resistance we had written down this thing, IR plus this thing. The EMF of the battery would be potential difference across the load plus the potential difference across the internal resistance. So what I'm going to do, I'm going to make I the subject. So it would be E divided by small r plus capital R. I hope you could see when I have skipped one of the step. I should have taken I common on the right side. Then I would have been left with r plus capital R, and then r plus capital R was shifted on the other side. Now what I'm going to do is I'm going to insert this expression for I in this formula all the way over here. So let's see what we get. So the output power equals I square. I'm not going to write I square, rather I'm going to write this thing. I square, this is the expression for I, times R. And if I do some rearranging on that, it could be written as P out equals R divided by R plus capital R whole square times E squared. And once again, I might have skipped one of the step here, like you could just take square on both sides, numerator and denominator. In numerator we get E square, but I've written E squared all the way on the right side, and denominator written as it is, and R was written on the left side. That's it. Now, like I said, for the maximum power, for P maximum, internal resistance should equal to the load resistance. And this is the expression that we're going to use in order to find the power across the load resistor. And you see, how is it different from the one that we study in O levels? In O levels, we simply say P equals to I square R. And if current is not given, we could find the current as well. But the thing is, in that formula in O levels, we don't incorporate the internal resistance. So you do not have this thing in O levels. And what do you have instead? So since we say there is no internal resistance, there is no concept of internal resistance in O levels. So what I can say is R equals to 0. There is no internal resistance. So this is what we do in O levels. So if R equals to 0, and I write down the same expression, it would be R divided by small r is 0, so you'll be left with R square times E square. Now one of the exponent would be cancelled out, and what are you left with? You will be left with output power equals to E square divided by R, because one of the power is cancelled out. And after that, in O levels we say EMF simply equals to the terminal voltage. So whatever the EMF is, you're going to get the same voltage as it is, so V square over R. And this is what we study in O levels. So this is just a simplified form of the actual formula. So the expression P equals to V square over R is a simplified expression for this actual formula. This is the standard, this is the actual formula that incorporates the internal resistance as well. But if you assume the internal resistance to be 0, this is what you will get on the right side.